Hello, hi. My name is Huzaifi by Yusri. My metric number is B122320057. So today I will present to you about oscillator 1. So this is specification of oscillator 1. So the oscillator type that we will use is wind bridge oscillator, and the resonant frequency of wind bridge oscillator must be 1 kHz and the DC supply is 15 volt. So this is our circuit of oscilloscope 1. So as we can see in the circuit, they have three resistor and one variable resistor. So and they have two capacitor of it. Also we use op amp. The type of op amp is 741, and we can see wind bridge oscillator must have RC series circuit and RC parallel circuit. So this is calculation of oscilloscope 1. So for calculation of capacitor, we have decided to use R1 and R2 equal to 10K. So as we know, when to get a good sine wave, we need to make sure the resistor and capacitor in RC series circuit and RC parallel circuit must be same. This is because when it is not same, the sine wave that we will get is not good, which is maybe can get a distortion. So to get it good of sine wave, it must be same value of it. So for this circuit, I have decided to use resistor equal to 10K, which is 10 kilo ohm. So by using resonant frequency formula, which is 1 divided by 2 pi times RC, we can use the formula to get the value of capacitor. So the formula will be C equal to 1 divided by 2 pi times resonant frequency times resistor. So the calculation is C equal to 1 per 2 pi times 10 kilo ohm times 1 kilohertz. So the value of capacitor that we will get is 15.92 nanofarad. So for gain, we have decided to use a value of R4 equal to 20K. So to get a gain equal to 3, the value of R3 must be times by 3. So as we know, the value of R3 must be greater than R4. For get sine wave good, must be lower than 3. If gain equal to 3, the calculation will be gain equal to 3 times 20K divided by 20K equal to 3, and for gain equal to 2, R3 must times by 2. So the calculation will be gain equal to 2 times 20K divided by 20K equal to 2. For gain equal to 3, R3 value is 60K, and for gain equal to 2, value of R3 is equal to 40K. So next is circuit simulation. So from this circuit, I have used gain equal to 2. That we can see when we use gain equal to 2, the sine wave that we get is good without any distortion. Variable resistor that we have set is 40%. 30% of 100 kilo ohm. So from this oscilloscope, the resonant frequency that we get is 1.008, which is same like what specification of oscilloscope 1 need. So when we use gain equal to 3, the sine wave that we get is not good, which is have distortion. So that's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Iskandar bin Gaffar. Today I'm going to explain about oscillator 2. First, the specification for oscillator 2. The oscillator type is wind bridge oscillator, and for the DC supply is VCC plus minus 15 volt. The resonant frequency is 20 kHz. Next, the calculation for oscillator 2. First thing first, we should calculate the resistor. So we assume capacitor C on oscillator 2 is 1 nanofarad and resonant frequency is 20k. So we know that resonant frequency equals to 1 over 2 pi RC. So we just substitute R equals to 1 over 2 pi times 20 kilo times 1 nano, and the answer is 8 kilo ohms. So the resistor 8 kilo ohms is the standard resistor we use in the simulation. Next, with the first calculation that we calculate, we recalculate the frequency with the calculated value of R and C to check whether it matches the specification. So resonant frequency, we know the formula is 1 over 2 pi RC. So we substitute resonant frequency equals to 1 over 2 pi times 8 kilo times 1 nano, and we got the resonant frequency 20 kilohertz, and 20 kilohertz is matched with the specification for oscillator 2. Next, we calculate the gain. So the formula of gain is AV equals to 1 plus RF over RA. So 3. So AV is 3. So 3 minus 1 equals to RF over RA, and 2 equals to RF over RA. And now we got the formula for RF, which is 2 times RA equals to RF. For the calculation of resistor frequency, we use the formula that we got earlier, which is 2 RA equals to RF. So RA, the value of RA is 50k. So 2 times 50k equals to 100k. So we can use 100 kilo as resistor frequency. So this is the simulation in multisim for oscillator 2. First, the resistor 2 is 8 kilo ohms and C1 is 1 nanofarad. C2 and C1 is the same, and R1 and R2 also the same. So we use the op amps, and the VEE is negative 15 volt and the VCC is 15 volt. RA is 50k kilo ohms and the resistor frequency is 100 kilo ohms. So this is the output for oscilloscope, and we got that frequency is 17.9k, and it is almost the same as the specification resonant frequency 20 kilohertz. So V peak to peak is 15.4 volt. So that is the result for oscillator 2. Thank you.
Assalamualaikum and a very good day to my dear lecturers of Teknik Suara. My name is Mama Irsyad bin Fithri Aziz, and I'm going to be continuing my part for the group project. So I have been assigned to complete the active low pass filter using the second order Butterworth filter. So based off of the given parameters, which is using a second order Butterworth response and a given cutoff frequency of 8 kilohertz, I have constructed the circuit down below in MATLAB. So first I'm going to show the calculations to completing this in finding the resistor values for this circuit. So from the Butterworth filter vector value, we know that the given quality factor is always and will be 0.707, and as you can see, Q equals 0.707. So the quality factor Q is equals to 1 over 3 minus AF. Okay, so from here, what we can do is we can find gain. So the given value of Butterworth filter 0.707, we will equate to the quality factor formula. So 0.707 equals to 1 over 3 minus AF. And by just using simple mathematical terms, we move around. So AF, we bring it to the left side, and we will minus it with the given value, and then From here on out, we will change it to RF over R1. So 1 plus RF over R1 equals to 1.586, and then we just move 1 to the right side, minusing the value of 1.586. We will get the given value of RF over R1 equals to 0.586. Okay, so from here we assume that the value of RF is 820 ohms, which is in standard resistive value used in the simulation that we will show a little bit later. So from the value that we've gotten so far, RF over R1 equals to 0.586, we will equate 0.586 equals to RF over R1, and then just changing the value of RF with the assumed value of RF, which is 820 ohms. So 0.8586 equals to 820 ohms over R1. So move R1 over to the left side, and you will divide 820 by 0.586, and then we will get the value of R1, which is 1.399 kilo ohms, which is in the standard resistive value that we use in the circuit. Okay, so from here, what we can do next is finding the rest of the values. So we assume that the capacitor C equals to C1 equals to C1 equals to C2, which is equals to 22 nanofarad, and the given cutoff frequency must be in 8 kilohertz. So using the formula for frequency, cutoff frequency FC equals to 1 over 2 pi R times C. So we can change the position of R and FC. So R equals to 1 over 2 pi FC times C, and then we just substitute in the values that we've gotten so far, which is R equals to 1 over 2 pi FC, cutoff frequency, which is 8 kilohertz, 8, and then the capacitance of C, 22 nanofarad. So we will get the value of R equals to 904.29, which is about the same value as 910 ohms, which is again the standard resistive value that we have used in the simulation. And from here, we know that R equals to RA and is also equals to RB. So from there, the summing of calculated values that we've got so far is the RF is equals to 820 ohms, R1 equals to 1.3 kilo ohms, and obviously capacitance C equals to C1 equals to C2 is equals to 22 nanofarad, and R equals to RA equals to RB is also equating to 920 ohms. So now we're gonna go ahead and take a look at the circuit. So this is the circuit that I have constructed using the values that we have assumed. So now we're gonna go ahead and run this the simulation, and then first we're gonna take a look at the volt plot. So at volt plot, we're gonna go straight away to the value of around 1.352 dB, and as you can see, it is equating to the kilohertz of 8.09, which is about the same as 8 kilohertz. Okay, so then we're gonna go take a look at the oscilloscope to view the values of channel 1 and channel 2. So as you can see, the channel 1 peak to peak is equals to 32.5 volts. The channel frequency is obviously 4 kilohertz, and then channel 2 frequency is 4 kilohertz, and the channel 2 peak to peak is 28.2 volts. All right. So that is pretty much from me, and then we move on to the next part. Thank you very much.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a good day to you. My name is Ahmad Hasif bin Rosman, and my matrix number is B122320014. And in this video, I would like to talk about the full wave rectifier. So moving on. So this is my circuit build, and as you can see, I have one voltage source, which is an alternative current, which shows an input of 9 volt RMS at a frequency of 1 kilohertz. This represents the AC main voltage to the converted DC. So as for the bridge rectifier, which composed of 4 diodes, and is arranged in a bridge configuration. Diode D1, D2, D3, and D4 works together to rectify both halves of the AC waveform. So thirdly, you see the smoothing capacitor C1, which has a value of 1 microfarad. And lastly, we have R1, which is the resistor, and that has a 2.4 kilo ohm of value. As for the operation, at the AC input, the AC voltage source V1 delivers a sinusoidal voltage of 9 volt RMS at 1 kilohertz rectification. As for the rectification process, during the positive half cycle of the AC input, diode 1 and 3 conduct, allowing current to flow and generating positive voltage across the load resistor. And during the negative half cycle, diode D2 and D4 conduct, again producing a positive voltage across the load resistor. This results in both half of the AC waveform being utilized, producing a pulsating DC voltage at the rectifier output. So as for the smoothing operation, the pulsating DC voltage from the rectifier is not a stable and contain ripples. The smoothing capacitor charges to the peak voltage of the rectified signal during the peaks and discharges slowly during the troughs, effectively filling in the gaps and smoothing out the voltage. This significantly reduces the ripple, resulting in a more stable DC output. So as for the load application, the smooth DC voltage is then applied across the load resistor R1. The voltage across R1 represents the final DC output of the power supply, suitable for powering electronic circuit that require a steady DC supply. So, moving on, as for the calculation and measurement, two multimeters is used, which is XMM1 and XMM2. Both reading shows approximately 10.262 volts, indicating that the DC output voltage after rectification and filtering. So, as for the calculation, the peak voltage of the AC input can be calculated from the RMS voltage using the formula Vrms times square root of 2. Given Vrms is 9 volt, so we just put in the value and we get 12.728 volts. The DC output voltage can be calculated considering the voltage drop across the diode. In a full wave rectifier, there are two diodes drop, which typically drops around 0.7 volt. So we will use the formula VDC VP minus 2 times voltage diode. So we know that by calculating the VP, we know VP is 12.728 volts, and at 1.4 volt here, we know that a voltage diode is 0.7, so 0.7 times 2 is 1.4, so 12.728 volts minus 1.4 volt, and we get 11.328 volts for the waveform that we get from the input and the output. We can see at the input we have a sine wave, which is the AC input. At the left oscilloscope, we know that the V peak at the V positive peak is 12.728, while the negative peak is negative 12.726. Now, we know that positive peak at channel B is 12.048, while the negative peak is 8.536. So, the waveform at the DC voltage, the waveform shows that the rectified output voltage is fairly stable and around 10 volts, consistent with multimeter readings. There is a small ripple present, which is typical in rectified signal even with filtering capacitors. This ripple is significantly lower than the input AC signal amplitude. So that is all for me. Thank you.
Hi and salam sejahtera. My name is Muhammad Azfariezuwan bin Gaffar. So I'm going to present about the voltage regulator and load. So as you can see, this circuit is a voltage regulator using a op-amp shunt, which is the output voltage is 5 volt and the load rated power is 1 watt. So we are going to the next slide. So the calculation for this voltage regulator and load is, first we assume the VZ on the Zener diode is 2.5, and the Vout is given, which is 5 volt. We use this value so that we can get the ratio of R1 and R2. As can you see here that we use the value for R1 and R2 is 10 kilo ohm, which is the ratio is same, which is 1. And back to here, with the first calculation, we know that R1 and R2 must be the same, so we assume R1 equal to R2 equal to 10 kilo ohm. So next, with PO, we can calculate the RL by 5 volt power of 2 divided by 1 volt, so equal to 25. So the RL we got here is 25 ohm. So here the value that we use for the RL, which is 25 ohm. Next, to find the value of RS, we need to find the value of IS first. In op-amp shunt regulator, the current through the shunt resistor is equal to the load current. This means we need to calculate the IL to get the IS, which is V out over RL. So to get IS is we use this value 5 volt divided by 25 ohm. So we get here 0.2 ampere. To get the value of RS, we need to divide the voltage drop by IS, which is, before this we get it. The voltage drop is the difference between V in and V out, and the V in on circuit simulation is 10.2. So as you can see, V in minus V out over divided by IS, which is 10.2 volt minus 5 volt divided by 0.2 ampere, which is equal to 26 ohm. But we use 27 ohm because it is the standard resistor value that we use in the simulation. So you can see here we use the RS, the value of RS is 27 ohm. The R3 is the resistor that leads to the limit current through the Zener diode. So assuming the breakdown current on Zener diode IZ equal to 10 million ampere. To maintain its voltage, we can calculate the value of R3. So R3 is equal to V in minus VZ divided by IZ. So 10.2 volt minus 2.5 volt over 5 milliampere. So R3 we get 1.54 kilo ohm. But for the multi-sim simulation we use 1.5 kilo ohm. So here are all the values that we calculated. So R1 and R2 is equal to 10 kilo ohm, RL is 2.5 ohm, IS is 0.2 ampere, RS 26 ohm, R3 1.5 kilo ohm. So here the simulation for voltage regulator and load for our circuit. So here the value that we get for V out and PO. So that's all from me.